Hello, my name is Paul Hoffman, CEO of Controls Research. Here I am presenting a simulation of a gas turbine jet engine using the new software tool SimTurbo. In this view, we see the palette. The palette contains this empty space where we will create our design. And over here are the tools that we would select to create the design. So for this design, we're going to design a gas turbine turbojet engine, and it's pre-selected. So what I'll do is click on here and click turbojets. Click here, and in particular we're going to create a simulation for a GE J85 engine. Next, we're going to go into constant nozzle control. And the control type that we'll select is a PID, or proportional integral derivative. We open up the system. And here it is, our simulation of the gas turbine jet engine. What I'll do is close the tools menu so we get more palette grid space. And so here we see the entire system. And what it's made up is of the different components for the controls, sensors, set points, actuators, and the engine. Over here in the pink are the set points for the throttle and the temperature limit. The throttle will change as a function of time and is pre-programmed for this particular example. In other examples, we can manually select it, but you can see this A stands for auto mode, automatic mode of the throttle. The temperature setting is a limit, and we have it set at 1640 degrees Fahrenheit or 2000 Rankine, so that the exit temperature of the turbine does not get above 1640, because if it does, then we'll start on a real system, different components will start melting, like the turbine blades could start melting. And so here in the blue is our control system, and we have two PIDs, or proportional integral derivatives. All of the software is basically encapsulated in these two modules, so that the user does not have to worry about that. All he would do is select the PID that he'd want. He would connect them. For instance, in this case, the speed PID and the temperature PID are min selected, so that we get the minimum fuel rate to control the engine. We also have a limiter, a WF over PS3 limiter on the system. Starting fuel, the igniter control, a variable stator vane set point, and here we have a compare where we're actually comparing the throttle to a to a threshold to enable the action of the igniter. When I click on here, or actually of the torque starter. So when I click on here, it shows the connection of the torque starter. And we could either have this permanently set, or as I show, hidden in the background, where if you highlight it, it'll show the connection to the starter turbine torque starter. In yellow, we have the sensors that are taking measurements from the green components and then feeding those measurements into the control system. So for instance, this is a turbine exit temperature sensor, inlet pressure sensor, the exit pressure sensor from the compressor, the physical speed sensor, and these other are groupers and muxers and demuxers for the sensors to enable more compact collections of the sensor signals and feeding into the controls. The controls then send their commands to the actuators. Here we have the fuel actuator, which we've selected to be a second order fuel actuator. The same with the variable stator vane actuator, is second order. We have the option of first or second order. And finally, we get to the engine components. The inlet, compressor, combustor, torque starter, turbine, the duct downstream of the turbine, and the nozzle of the jet engine. And remember, we selected a constant nozzle nozzle system. We see here in the blue are the connections, the lines showing the airflow going from the inlet to the compressor. This dot here shows that the inlet is connected to ambient. Similar to these dots, the compressor here is overboarding flow into the ambient. And here, out of the nozzle, this shows that the nozzle sends the combined fuel or sends the airflow through the nozzle to the ambient. So here we see that the fuel actuator sends the yellow fuel line into the combustor. It's ignited with the igniter control. All of this is properly timed and based on the temperature measurements inside actually temperature measurements from the turbine would determine when we ignite the combustor. Temperature and fuel, temperature and speed. Here we have a torque starter, and as you probably know, a turbojet is not self-starting, so you need an electric starter, here represented by the torque starter component, to start the system, and then when you get to a certain speed, in this case 9,000 RPM idle, the torque starter is disconnected from the system, and you have a direct connection in a shaft from a compressor to the turbine. And then this flow again goes from the turbine to the duct to the nozzle and produces thrust at the back end of the nozzle. For each of these components, if you double click on them, it brings up a screen where it allows you to make different parameter selections. We can change from auto tune to manual tune and so forth. Change the proportional, integral, and derivative gains. Now, each of these tabs, so we're looking at the design tab here. And again, this was auto designed. We could have used the other tools tablet to do our design, but we selected an auto design for the J85 engine. This tab shows the ambient conditions, and you'll see as a function of time, we can see how these parameters such as ambient temperature, ambient pressure, and so forth are moving. And then we have a plot of the flight envelope versus time, which shows both the altitude in blue and the flight Mach number in red. And you see this, it has two dots. The blue dot is hidden behind the red dot starting at 0, 0. But as we go on in time, the two will move. We have the various engine parts, the inlet, and we have the different parameters of the inlet, which we'll see updating in time here. We have a graph, and this graph will show the stagnation pressure ratio of the inlet as a function of time. We have a compressor map, and you can see it's the standard compressor map where we have a surge line in red, a choked flow line here, and we have constant speed lines. Well, actually, these are constant efficiency lines right here in black, and then the constant speed lines here in blue. So as the speed goes up, and this is in corrected speed, as we also have corrected flow rate on the x-axis and pressure ratio on the y-axis. And then here we have all the parameters which will be varying as we progress in the engine. This shows the same type of situation for a combustor. We're able to select the type of fuel that we use, which is, in this case, we've selected jet fuel A. The turbine, and we have a turbine map where we show corrected flow rate versus pressure ratio, isentropic efficiency versus pressure ratio, and also as a function have different speed lines. And again, we show all of the parameters here as we move in time. The duct, similar. Nozzle, here we show the nozzle thrust, the net vehicle thrust, and the jet velocity as a function of time. The torque starter, it shows when the system starts, the torque starter will be in operation, and then After it starts, you'll see that the torque starter is off. Have different plots all combined here to make it easy for the designer to look at the system and the different components in one spot. You can look at all of the different components and some of their major parameters as a function of time. Same with the actuators. Fuel actuator, variable stator vane actuator, and we plot both the fuel and the VSV actuator on the same tablet so we can see them at the same time. Then here goes the various controls. Again, we have the variable stator vane set point, the starting fuel, igniter control. Then we have the different PIDs. We have two PIDs here, speed PID, temperature PID, and we have a WF over PS3 limiter. Then we plot the speed and temperature here together so you can see how they're working in coordination. All the sensors are plotted as a function of time. And you can also look at their parameters. So for all of the different sensors. We also have here table of the various states and initial conditions, where we show the values, the initial conditions. You can see it's color coded. For instance, blue shows the control PIDs. This orange will show the different actuators, the fuel and the variable stator vane actuators. The green shows the different components, the inlet, compressor, combustor, even the shaft, all the way down to the nozzle. And then yellow shows the various sensors. And these values will change as a function of time. Here we've represented steady state conditions to show in steady state what the variable values of the systems are. In green, we have the inputs. So altitude, flight Mach number, delta temperature, ambient, relative humidity, the turbine physical speed, compressor margin, surge margin, parasitic flows, flow ratio, overboard flow ratio, variable stator vane setting, nozzle thrust area, nozzle expansion ratio, the duct pressure loss ratio. Now, in blue, we show the various outputs as a function of time, starting with fuel rate, combustor fuel rate, and then for each component, such as the inlet, compressor, combustor, so forth, we show the mass flow rate going through the component, the exit temperature, exit pressure, and so forth for all of the components. all the engine components, that is. And then we also show in steady state again thermal efficiency and the other different efficiencies, and the thrust specific fuel consumption, the net thrust, and the engine pressure ratio. We'll show later the cycle, the thermodynamic cycle, which is of course the Brayton cycle. Different performance plots, including the thrust specific fuel consumption and thermal efficiency, parametric analysis, and here's an interesting tab where we go through and for instance this engine, the J85, basically show some of the history of the J85 engine, some of the basic system details, and then a picture of the J85 engine, and then two representative applications. And of course the J85 engine was a military jet engine, and for your example, the reason I chose the J85 is there's a lot of information on the internet regarding. Now let's go back to the controls plots. And again, we're looking at the speed PID and the temperature PID. We'll start a simulation. And you can see we started off at 0 speed, and the torque starter ramped up the system, and now we're at a steady state point around 9,000 RPM. Then we ramp up to 12,000 RPM, and you could see how the temperature is behaving. It's pretty stable below the set point or limit. And you can see that the speed is changing, the set point is changing, and the feedback speed is following. Now we'll look at some other graphs. Go to ambient, and you can see the aircraft is going up in both altitude and flight Mach number, and it's following this trajectory. Look at the different engine parts. The inlet, we're looking at the stagnation pressure ratio, and it's holding steady at about 1, which is normal. The compressor map, so then the compressor operating point, we went through a transient there where it was going back and forth, but now we're basically at steady state of 15% surge margin. So we're in good surge margin of around 15%, and it just changed again the operating point. But we still have a surge margin of around 15%. And again, on this graph, we see the compressor mass flow rate, the pressure ratio, the surge line in red, and the black dot that we're following to show the operating condition. The efficiency lines in black, and the speed lines increasing in blue. On the combustor, we can see the combustor temperature. We have the combustion temperature and also the exit temperature of the combustor in blue. Down here we show the corrected fuel rate, fuel flow over exit pressure, static pressure. And again, we see the different variables changing as a function of time. Turbine. We're looking at the turbine map, and you can see a lot of oscillation. The reason is because we have very sensitive slopes on the turbine map. Inside the duct flow downstream of the turbine, we're measuring both the flow rate in the top graph and also the exit temperature in the duct. The nozzle. You can see the thrust of the nozzle. The nozzle thrust and also the jet vehicle thrust in red. Then down here is the flight velocity going at around 1700 feet per second. Torque starter is off because we started the engine, so it's off. Then we can, like I said, a designer can look at all of the plots at the same time to get a feel as to how the engine is behaving overall. Then we look at some other things we look at the sensors. You can see the turbine physical speed sensor and the black dot here where we're plotting the sensor voltage versus speed, and we can see we're at around, I'd say, what does it say? It's around 15,800 RPM. Compressor inlet temperature. At ambient, as you go up in altitude, the ambient temperature goes down. Compressor exit pressure. Compressor inlet pressure. Turbine exit temperature. States in the inlet conditions. Again, steady state, that remains the same in steady state. But a very interesting set of plots are the thermodynamic cycle plots shown here. So this is the standard Brayton cycle. You can see we start here at blue at the ambient. We go through the compressor to the highest pressure in the system. We go down in pressure as the volume, specific volume increases across the combustor. Then we expand across the turbine. So again, we're dropping in pressure significantly, but we're expanding the specific volume. And then across the nozzle. And we have different plots we can show. We can show the TS plot, temperature versus specific volume, pressure versus specific enthalpy versus specific entropy, and specific internal energy versus specific entropy. We can look at different performance plots, such as this shows the stress-specific fuel consumption, the thermal efficiency. See, this engine is running at about, what does it say, 37% thermal efficiency. We won't look at the parametric analysis. Still doing work on that. And again, we saw this before. This is just some information regarding the engine. So what you've seen is an overview of a simulation of a J85 engine using SimTurbo. Hope you enjoyed it. And if you're interested, please go to our website, simturbo.net. Thank you.